So before we jump into examples, we need to establish some strategy for how we are going to describe solution sets of homogeneous equations, and as we'll later see, non-homogeneous equations as well. And now we've already begun to establish this strategy. We are just really perfecting our methods here. So we are going to be given a system of linear equations, a homogeneous system, if you will. And the first thing that we want to do is check to see if that system has a free variable. And how are we going to do this? Well, we are going to row reduce the augmented matrix to echelon form. So we row reduce the augmented matrix. And if we're working with a homogeneous linear system, that will be matrix A augmented with the 0 vector. And we're row reducing this to echelon form. Now we don't need to go all the way to row reduced echelon form yet, because we just want to know, is there a trivial solution or does a non-trivial solution exist? So what are the things we're checking for? Free variables. So case 1, let's suppose that there are no free variables. What does this tell us about the solution set? Well, if there's no free variables, then that means it's a trivial solution. Versus, if at least one free variable exists, then we know the system has a non-trivial solution. So if there are no free variables, meaning that each row has a pivot position, we know that our homogeneous equation will have a trivial solution, a unique solution, the 0 vector. If at least one free variable exists, we know that our homogeneous equation has a non-trivial solution. So after this, we continue our row reduction so that we can write the solution set in a parametric vector form. So to do this, we want to express each basic variable in terms of any free variables that are appearing in the equation. So we express each basic variable in terms of any free variables that are existing, or any free variables that appear in the equation. After we express each basic variable in terms of any free variables, we can then write the general solution, vector x, as a vector whose entries depend on the free variables. So we can then write the general solution, or vector x, as a vector whose entries depend on the free variables. And we should put if any exist, simply because we could still have that non-trivial solution. So we write that general solution, vector x, as a vector whose entries depend on these free variables, if any free variables are existing. Last but not least, we can then decompose the general solution, vector x, into a linear combination of scalar valued vectors, or vectors with numerical entries, using the free variables as the parameters. So we can then decompose our general solution, vector x, into a linear combination of scalar vectors So vectors whose entries are all numbers. And this is using the free variables as the parameters. So this is the same method that we've been looking at, expressing each basic variable in terms of any free variables that may appear in the equation, then writing that general solution vector x as a vector whose entries depend on these free variables, if any free variables are appearing. And last but not least, we then decompose that general solution vector x into a linear combination of scalar vectors using the free variables as our parameters. Now, step 3 applies to what we just saw with the span of a set, and that is to describe the solution set when applicable. So in order to describe the solution set, we're going to use the column picture of the solution set to provide a geometric interpretation of our general solution. So when applicable, we will use the column picture of vector x to provide a geometric interpretation of the solution set. So this is our strategy. And again, we have been perfecting this thus far, this course together. We are going to be checking our system for the existence of free variables. We then want to go ahead and write the solution set in a parametric vector form. Now, to really help us describe that solution set or to provide a geometric interpretation of the solution set, we want to decompose the general solution, vector x, into that linear combination of scalar valued vectors, or vectors whose entries are numbers, using those free variables as the parameters. So let's put this strategy into practice and look at some examples.